questions about. So this one I did a while, like right at the start, but I'll put a link to it again. I'll do that now. So the ones that I have in blue text are things that I added after I looked at the revision of the test. Okay? So some additional things that you should make sure that you know how to do. So when we talked about bases, you need to be able to convert from one base to another. Okay? So for example, from binary to decimal, from binary to hex, from hex to binary, from hex to decimal, from some random base to some other random base. Yes?
Will there be solutions for the review so we know that we got the answer?
I do have solutions for this review. Yes. I'll post a link to that too.
When you say write a function, do you mean just like pseudocode function?
Yes.
Yeah, we need to work out our Ruby and JavaScript.
So pseudocode's fine. You can write it in like, we're not going to run the code. Okay? We're going to look to see if it makes sense. Yeah.
Will we
So-
have access to our will we have access to our own code?
Yes.
Okay.
Stuff
So if we've already written
Yes.
a function,
Yes.
copy it.
You can.
I know, this works, I think.
Yeah, look, so if you've worked it out already, and you've already written a function that does it, then by all means. Okay? Because all you need to do here is demonstrate your understanding of the concept. So if you've written a function to convert between bases, then obviously you understand the concept, right?
What if it's in a language you guys don't know? Like, what if it's in
Go. I didn't scratch.
We it's Scratch. That's very good. Okay, so how do you think you would convert from one random base to another? Yes, exactly. First you convert to base 10, then you convert to the other base. Okay?
Is it good enough to write pseudocode that's just like 2s10 and then 2s2? Or
No.
no?
Don't use built-in functions in your pseudocode. No. No, because what we're testing there with that question is, do you understand how you go from one base to another?
I mean,
Okay.
if you're showing that you would change it to decimal and then change it to the correct one, isn't that kind of
No,
showing? But it's
it
not
isn't.
that.
No,
Right.
so it's not. Yeah, it's not showing that you understand that to go from one base to decimal, then you multiply each number in the place by the place value for that place. Yes, and you sum those products together, and that's how you go from one base to base 10, right? And to go from base 10 to another base, then you have to do iterative division and keep track of the remainder. Yes? So you need to demonstrate that you understand that that's how you do those conversions. Okay? Writing pseudocode to show that is fine. All right? Or, like I said, if you've already written a function to do it, you can copy and paste that into the test.
Is it giving you a pen and paper test?
No, it's a Canvas test. Yeah, just like Ruby test. Okay? You can use IRB, you can use VS Code, you can use a calculator, you can use pencil and paper, and I encourage you to. I'm going to remember to ask Ash to make sure we've got pencil and paper in the classroom for Wednesday.
If we've written down notes in a book like this,
Yeah.
do you use that?
Yep,
So it's kind of open book. Like,
it is.
if you want to look back on a lecture file or something.
Yes.
Yeah.
Okay, so that's, anybody have questions about converting bases? Everybody good on that? Do we need to go over that? All right. Understanding digits in a number system. Okay? Understanding if we're in base 4, how do I count in base 4? 0, 1, 2, 3, 1, 0, not 10. 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2. If I'm in a base higher than 10, say I'm in base 12, how do I count in base 12? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. 1 0, 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, 1 8, 1 9. 1 A, 1 B. 3 0. Does that make sense to everybody? Remember we had this sheet? Sorry about that. This sheet here, remember we did this? So we did a base less than 10 to see how the numbers, how we count in that base. A base bigger than 10 to see how we count in that base. So you need to understand that, how to count in a particular base. Okay? Boolean logic. Truth tables. So you'd want to make sure you're familiar with the truth tables. You well understand or, and, exclusive or. And understand what not does. Not's just the opposite, right? Of whatever the input is. Okay? Knowing how to combine these. So, did I add more to this? I didn't. So if we had, for example, if we had, for example, P and Q XOR P. So if we had P and Q, and first we calculate P and Q, and then we take that result and XOR it with P. What's the result of that? So being able to string together
Is it
these Boolean.
the same P in this?
Yeah, so the same P. So what you would do for this, this would be something like, so P, Q, P and Q, result XOR P. XOR P, yeah, that's fine. So if we had P, oops, that's not P, P, Q, P and Q, P and Q XOR P. Okay, so we have true, 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 false, false, true, false, true, false. Yeah, to set up all the possible combinations of P and Q. So what would be the results for this column, P and Q?
It's true. And then
True.
False. False.
Okay. Now, I want to compare P and Q with P. Right? So true XOR true.
False.
True XOR false.
True.
False XOR false.
False.
False XOR false.
False.
Did everybody follow that? In this column, I'm comparing this column. Where's the background? Oh, it's not up there, is it? How do I do this? How do you do?
Not there.
It's not.
It's behind your menu.
Is it?
Behind your right section. No, it's not. There it is. Over in the top right
This?
corner.
Is it this?
No, that's borders. There's a top right corner-ish. There's a bucket.
This? No. Top right. Why am I not seeing that?
Work bar.
Oh, right. Yes. Yes. So this and this is what gives me this. Okay? And we can string together as many of these as we want. Okay? You just have to do it one step at a time. Okay? Does that make sense?
What's the XOR? I think I missed out on this lesson.
Yeah. So let's do the XOR table. So P, Q, P XOR Q. So exclusive OR says that one or the other is true, but not both.
Right.
Only one of them is true. So if both are true or both are false, XOR is false.
Okay.
It's exclusive OR.
Right. Okay.
The regular OR is actually an inclusive OR, but we don't say inclusive OR. We just say OR.
Okay.
Okay?
It's like inclusive or is obviously like false and false is true.
So inclusive OR, true or false, is true.
Yeah.
False or true is true.
Yeah.
True or true is true.
And false and false.
And false or false is false.
I've got it. Okay.
Okay? But exclusive OR, true, exclusive OR true is false.
Mhm.
Only one or the other.
Okay. Okay.
Okay?
True. True. Yeah.
Any other questions about truth tables? Okay, bitwise operations. Bitwise operations. Do you guys remember this? I really should open the answer sheet instead of answering in the sheet.
Very interesting.
It's basically doing the truth table, but using the values given rather than
Yeah, one bit at a time, right? So let's look at one bit at a time. Hence, bitwise operations. Okay. So I don't know if I can't remember if I added the answers for. There we go. Okay, so if we wrote it out in a table, which might make it more clear. 1, 2, 3, 4. So we have 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1 for the first number. Yeah? Center these because it'll bother me otherwise. And the second number is 1, 1, 0, 0. Okay? So with a bitwise logical operation, I look at each bit and I do the operation between those two bits, where 1 is true and 0 is false. Yep? So I look at the first column, 1, and the operation I'm doing is and. 1 and 1. Is that true or false? So I put a 1 there. 0 and 1. 0 and 0. Super false. 1 and 0. False, because for and, the only way I'm going to get a 1 here is if I have a 1 for both numbers in that place. Otherwise, I get a 0 with and. Yep. What about for or? Yeah. So for or, one or the other has to be true. One or the other, I have to have a 1 in that place. So in the first place, I have a 1, so I know there's a 1 in the first place. In the second place, I don't have a 1 in the left number, but I have a 1 in the right number. So that second place value is going to be 1. In the third position, I have a 0 in both numbers. So it's going to be 0 in my result, my bitwise operation result. And in the last place, I have a 1 here, so I'm going to have a 1 there. Exclusive OR. In the first place, I have a 1 in both numbers. In exclusive OR, that's false. So that's a 0. Okay? I'm only going to have a 1 where I only have a 1 on one side. Okay? So you can make tables for these to make sure that, and on the test, like I think there's some bitwise operations. I'm pretty sure there's bitwise operations on the test. Just make the table. Yes.
Is this a show your work kind of test or just your answer?
No, it's just your answer. Now, if there's the potential for partial points, then you should show your work, right? So I added another one here. 25 and 13. These are decimal numbers.
Correct.
In order to do bitwise operations on them, I'm saying these are decimal.
They're not in base 6.
They could be, right?
Yeah.
So on the test, if you have a bitwise operation between two numbers and it doesn't tell you the base, you can assume it's decimal. Okay? And that's true in general. If you see a number and there isn't an explicit indication of the base, and it's not obviously binary or hex, if it's obvious, if there are only zeros and ones, and it's like a string of 8 zeros and ones, you can assume it's binary.
It's not 1,111.
Probably not.
No?
Okay? If it's got letters in it and they only go up to F and there's no indication of the base, assume it's hexadecimal. If it looks like 25 and 13 and there's no indication of the base, assume it's decimal. Assume it's decimal. Okay? So in order to do a bitwise operation on something that is not in binary, you must first change it to binary. Then you can do the bitwise operation, and then you can convert it back to decimal.
If the word add is on the test, do we assume that it's the word add or hexadecimal?
I'm going to leave that one to you, Leah. Okay. So I haven't solved this one yet. Shall we do this one together, or do you want to try to do it yourself? Hmm?
No preference. I prefer that.
You prefer what?
I prefer no preference.
Okay.
Let's do it.
All right.
Thank you.
I think this is actually D because I think I just created another letter when I did this. Yeah, okay. All right, so doing math in Word document is no fun. Let me just tell you. It's not easy. Okay, so 25 in binary. So what is your favorite way to do conversion from decimal to binary is a question. So I like to do the find the biggest power of 2 in it. But we can do it the other way. So let's just do it the other way. So 25, we start with 25 divided by 2, yes? To convert from decimal to binary. 25 divided by 2 is
12 remainder 1.
12, remainder 1. Does everybody follow that? Yes? 12 is still, bastard, 12 is still bigger than 1. I mean, yeah, so we have to say 12 divided by 2, which is 6, remainder 0. Yep. And 6 is still bigger than 1. So we say 6 divided by 2 equals 3, remainder of 0. 3 is still bigger than 1. So 3 divided by 2 is 1, remainder 1. Yes? 1 is not bigger than 1. So we're done. And what is our binary number?
11001.
Does everybody follow that? We start from the last quotient, the last result of the division. That's the first number. And then we go backwards through the remainders. So it's 1, 1, 0, 0, 1 in binary. Yep. That's our first number, 25. Let's do the second number. 13 divided by 2. 6, remainder 1. Then what? 6 divided by 2. 3, remainder 0. Then 3 divided by 2. Come on, you. 3 divided by 2. 1, remainder 1. Are we done?
Yeah, sure.
Because 1 is in base 2. Yes? And our number is
1101.
1101.
So you added 0 to make it 01101.
That's correct. Okay, because if we add a leading 0, we don't change the value of the number. If we added a 0 at the end, we would change the value of the number. We can't change the value of the number, so we add a leading 0.
And that's just to make the numbers match.
That's so we can do the bitwise
Okay.
operation.
Oh, yeah.
Yep,
Yeah.
because we have to have the same number of bits
Yeah.
to do a bitwise operation. Okay, so 25 and 13. So we're going to and these values. So now what we're doing is 1101 and 01101.
Just drop the 1 on the very first.
001. 11001 and 01101. Okay? So do you want to make a table? Okay, let's make a table. We'll make a table. We'll make a table. It's nice to do it methodically. How many digits? 1, 2, 3, 4, 5? 5. So we have 1, 1. Keep me honest. Make sure I type the right numbers in. 0, 1, 1, 0, 1. So like with everything in maths, it's all about like making sure you're precise, right? And checking over your work to make sure that you didn't transpose incorrectly, or, you know, it's a problem for me because my even when I write, you know, my hand doesn't move as fast as my brain does, and so I make mistakes. Okay, so we're doing and 1 and 0,
0.
1 and 1,
1.
0 and 1,
0.
0 and 0,
Super 0.
1 and 1,
1.
1. So our result here is 0, 1, 0, 0, 1, which could also be written as 1, 0, 0, 1. Yeah, we can take off the leading 0. What is this number in decimal? 9. How do we come to 9?
1, 1, 0, 2, 0.
So this is the same as 1 times 8, 2 to the third power. So everybody follow that? This is translation from binary to decimal. So this is the 2 to the 0 place, the 2 to the 1 place, the 2 square place, the 2 cube place. Okay? So, or the 1's place, the 2's place, the 4's place, and the 8's place. Okay? So I have 1 times 8 plus 1 times 1. So 1 times 8 plus 1 times 1, and that is 9.
In the test, if something like that comes up, will it explicitly state whether we have to convert it back to bits?
I don't know that it does, but convert it back.
Should I just convert it back?
Convert it,
Binary?
give it in whatever it's, convert it back.
Give it
So
in
if
the base
it's,
that given.
yes, give it in the base, give the answer in the base that the question is given in. Okay?
Unless it states otherwise.
Unless it says otherwise. All right? So there are multiple steps for that, right? Multiple steps. The first thing we have to do is convert from decimal to binary. 2 numbers. Convert 2 numbers from decimal to binary. Then we have to do the bitwise and. Then we have to take that result and do the conversion from binary to decimal. Okay? Now, there should, if there is something like this on the test, and the number should be small, so it shouldn't be like a huge exercise to do the, it's not like, you're not going to have like, 4,023 and, okay. So, practicing that is a good idea, okay? So just try to do the same problem yourself without looking at the answer and see that you get the same results, okay? It really is just practicing all of those things, isn't it? The bases work and the truth table all rolled up in one, right? Okay, know the rankings of the orders of complexity. Okay? What comes first?
Which way is first? Is it like least complex to most complex?
Oh, wait, let's talk about this first because I don't have this on the answer sheet, but there's some. bit shift. A bit shift is where we have a binary number, and we shift them in left or right. Okay, it's a pretty common thing in some applications of computer science to do this sort of thing. Okay, so the notation is that we'll have the binary number, we'll have left or right double arrows, and then we'll have some number, a decimal number, that we're shifting those numbers by. Okay? In practical applications, it's usually a small number, like 1, that we're shifting them left or right. Okay? So if we have this number, 0110, and we bit shift left one place, you just chop off the leftmost number and backfill with a 0. Okay? When we shift right, we chop off the right 2 numbers and backfill with 0. Alright? So if you shift left, you chop off the leftmost however many numbers and add that many zeros to the end. And if you shift right, you do the opposite. You chop off the rightmost that many numbers and add that many zeros to the left. Okay?
If you had a number that was bigger than, like, so we've got 4 digits there, the first one was 0110.
Yep.
It would ask you to bit shift, like, 17 places to the left, would it just become 0000?
So if you, so you basically, if you shift more than 3 here, then you end up with 0. Okay? But it's never like that. In practical applications, I mean, you could end up with 0, but you never, in practical applications, you're never shifting more than a small number. Yeah. Okay. Now, if what you're given on the left side of this double arrow is not a Boolean, you can't bit shift it. You have to turn it into a Boolean first. I'm not a Boolean. I said Boolean, I meant binary. You have to turn it into a binary first. If it's decimal, you can't bit shift it. You've got to turn it into a binary number first, a bit number, right? So you can bit shift it. Okay? So shall we do this one together? Okay. All right, so first step is to write 2 as a binary number. 1 0. And if we shift it 4 to the left,
0 0 0 0.
0 0.
yep, so we're just going to end up with 0, aren't we?
So we don't need to retain the number of places. Like if this was binary.
Yeah, so look, writing it like this,
If that was a 1.
actually, yeah, no, you're right. We don't end up with 0. Forgive me for that, because even if we have this, if we shift it to the left, then we're chopping off the rightmost.
So
I'm confusing
add 4
myself.
zeros on the end, so it would be 1 0 0 0 0 0, which would be like.
Yeah, but so we were supposed to retain. Yeah, okay.
Yeah, so if we had 0 0 in front of it, we could put as many zeros in front, we don't change that number, right? We can stick lots of zeros in front of that and not change that number. So, actually, just leave this one with me. Ignore this one for now because I'm confusing myself thinking about it.
So shifting it 4 places, make it
Shifting it 4 places.
yeah. Make it 32.
Yeah, exactly. So we have to shift the whole number 4 places to the left. So
So we're not limited by 4 places or anything. We just
Yeah.
add on. Yeah.
And as many training meeting.
yeah,
Yeah, that's right. It's good. Yeah, no, it's good to be there anyway.
yeah. Let me come back to this one just so I make sure that I can explain it more clearly than what I'm doing right now. So I'm obviously getting confused.
But essentially, what we're doing is converting to binary.
Convert to
then
binary.
Doing a bitwise operation on. both.
Not a bitwise operation, but shifting.
No, sorry, shifting. Then
Yeah.
Shift, and then we're doing a bitwise comparison between the 2 shifted binary
Yeah.
numbers,
Yes.
and then
Writing it as a decimal number.
right. Oh, okay, so that's not saying.
No. Actually, this is. I think this is. Maybe it is. Look at the test again, because if it's written like this, then it's expecting you to shift, convert to binary, shift them, do the and then write it back as a decimal number.
Okay.
Yeah.
It's going to be if it's shifting it to the left, the number will always get bigger. Whereas
The number
shifting
will-
it to the right,
Yeah.
will always get smaller.
Will get smaller. Yes,
So-
absolutely. The number should always get bigger. Yes.
So it won't,
Yes.
it won't ever become 0 if it's going to the left. It will just become, get rid of shifting it 4, it's going to go from 2 to like 16 or 32.
That's right.
Whereas 16 will go to 8.
That's right.
And then we just add present zeros and then do the end.
Yes. Yes. So 16 would be 1 0 0 0 0.
Yeah.
Yep.
And then it just becomes
And if we shift that to the right,
0, 1,
then it becomes 1.
0, 0.
Yeah. 0. It becomes 8, basically. Bit shifting 16 to the right 1 turns it into 8. Yes. Bit shifting 4 to the left would add 4 zeros to the end of it. So it would be 1 2 3 4. So that's 32.
So why would we do this in the real world?
So typically when you do it in programming, it's because you're, I'm trying to think of a non-obscure example. It is a way to do increasing powers of 2, for example, or decreasing powers of 2. So that without having to do the operation, so if what you've got is a binary representation of a number, or even, you could convert from a decimal to binary with a built-in, and then you could shift it left or right, and that would be a clever way to increase it or reduce it by a power of 2. Yeah. Probably it's used in data encryption. Yeah. Yes. So not my field, but you could bit shift to encrypt data, and then you could do the opposite shift.
Not very good encryption.
Probably not very good.
But yes.
Yeah. A very basic encryption, I guess.
So yeah, the final answer for this just be 0.
So, so it's because we would have,
You're doing an AND for
yes.
1 with 5 zeros and 0 0 1 0 0 0.
Yeah, so we need 2 extra zeros here. Yeah, and if we do an and,
It's just going to be 0 0 0.
then it's going to be 0.
Do we need to maintain the number of places? In that example, would 0 be correct?
No, 0 would be correct. Yeah, 0 is just 0. Yeah. 0 is just 0. So yes, you can think about it as shifting left means you're increasing the number by that many powers of 2. And shifting to the right, you're decreasing the number by that many powers of 2. That's really what you're doing.
And if you shift it to the right enough, it'll just stay at 0. Like if this one,
Yeah,
really
you'll
shifting to
decrease
left,
it down past 0. Yeah.
And then we just ignore it. Then it doesn't become like.
Considering negative numbers.
No.
So we should study bit shifting for exam.
There is at least one question about bit shifting.
Oh, that might be good.
How many questions are there?
It's tricky, right?
15, 16? Yeah.
Is it quite rushed? Like,
No, you have 2 hours.
okay.
2 hours.
How many questions did you say?
16?
16.
Yeah.
How many is that?
2 hours. And look, Rachel, I think this bit shifting question is like 1 point or something. Yeah. Yeah, it is interesting, and you'll come across uses of it potentially, but yeah. And I'll look at the test again to see if, I don't know that they actually do a Boolean operation. I can't remember if I wrote, I think it is. I think I did intend for this to be a Boolean operation. I can't remember now. When I wrote this, what I saw on the test.
Is this a group of tests?
Yeah. Okay, so what's the order, the rankings of the order of complexity? What's the first one?
Are we talking about least to most?
Yeah, least to most.
Constant?
Constant?
Logarithm?
Isn't logarithm like less than constant?
Nope. Constant
Constant stuff.
is the same no matter what size the data is. Logarithmic does increase with the data size, but it does so logarithmically, which is
Not
less
much,
than
but
linear.
still-
Opposite exponential.
yeah.
Yes. And then what's after logarithmic?
Yeah.
Linear. And after linear?
Quadratic.
Quadratic or polynomial. And after that?
Exponent.
Exponential. So know that order. Okay? Let's go back to this one. Did I not have... Is that sets in the right place? It's in the wrong place. Sorry about that. Okay. So for this code snippet, we have a function, a method, 'cause it's Ruby, method, and we have a nested loop. Yes?
So that's going to be polynomial.
We can just look at it and see it's going to be polynomial. Okay, just because it's a nested loop. But let's just look at it in more detail anyway. So we have an array of students, and within that student object, we have an array of classes. Can everybody see that? Is that clear to everybody? So we loop through the array of students, and in students we have this, in each student object we have this array of classes, and we loop through that array of classes. And then we say if the year property on student meets this condition, less than or equal to 9, and the class has this property active in this particular class in the list of classes, and that's true, then we return some results. Badly named method on that class. So the complexity of this is polynomial or quadratic, right? Big O of n squared. So what's a way that we could optimize it? Can anybody see a way to optimize that function? Method. So right now, yeah.
Do we
Go ahead.
need the for loops?
I can't really tell just without seeing how it's structured behind the scenes.
Could you just access each of those? Could you check to see if the student year is 9 before you do the next iteration?
We could.
So that you
We
don't
could.
just ignore anything that...
Yeah, because we checked 2 things here. So the core of this nested loop is we're trying to perform an action when the grade is less than or equal to 9, and they're taking this particular class, right? And what we're doing right now is that for every single student, no matter what grade they're in, we're looping through all the classes, right? No matter what the grade, we're still looping through every class. So even if we have a student that's in year 10, we're still going to loop through all the classes, right? So we could make it more efficient before we create this loop, by only doing this loop if the year is less than or equal to 9. Now, that would improve the efficiency of this method. Would it change the order of complexity?
No.
No, why not?
Still have nested loops, you're just going to be iterating over less students because you're removing some in that conditional statement.
And in a worst case,
You still do all.
Yeah.
we
And the
could
order-
still
order
have
of
to look at every
complexity.
student. In a worst case, because we don't know what our set of students is. In a worst case, all of our students are less than year 9. Maybe the database that we're working off of is for primary school or something, you know?
And
Like,
the order of complexity is always for the worst case.
always for the worst case, okay? So those are the concepts to understand from this example. That one, recognizing that because it's a nested loop, without, duplicate recursive calls to itself or anything else, it's just a simple nested loop, that it's polynomial or quadratic. So that's the first thing to recognize. The second thing to recognize is there is a way that we could make this more efficient. But the third thing to recognize is that this doesn't change the order of complexity, because order of complexity is concerned with the worst case. And we still may have to look at every class for every student in the database. Yes.
So without changing the way that the data is set up, is there a more efficient way of performing that action?
Not really.
Some things have to be quadratic.
Yeah. And look, quadratic is typically fine. Like we could, for example, order the records somehow, right? And incorporate some binary search. But the cost then is in ordering the records. You're just like shifting that somewhere else. Maybe it's more efficient to do that sorting in the database rather than in this program. And so it'd be better to sort in the database, and the records that we get are sorted, right? In some particular way. So it's possible that we could introduce some logarithmic complexity here if we make assumptions about the data being sorted. Yeah, but if it's up to us to sort the data, then you haven't gotten rid of any complexity, because sorting the data is going to it's going to make it quadratic again. Yeah. All right. Okay, so being able to recognize the complexity if you're given something like this, like you have 2 arrays of 10 numbers, call them A and B. What's the complexity of an algorithm to select the elements in A that are also in B?
Quadratic.
Yeah, and why is it quadratic?
Because you have to iterate through. Sorry.
Then I can say it at the exact same time.
You do it.
No, it's okay. For every element in A, you have to go through every element in B.
That's right. For every element in A, we have to look at every element in B. Because if we want to see for each element in A if it's in B, then we have to start with the first element in A, and we have to look all the way through B. And then we'll look at the second element in A and look all the way through B. And that could change again slightly if the B list is sorted, right? Then we could, maybe change it a little bit, but we'd have to make that assumption that the B list is sorted already. All right, matrices. So adding matrices. Everybody comfortable with adding matrices?
8, 10, 12, 4, 6, 8.
So the big thing is to make sure that we have matrices that are the same dimensions before we start, okay? And then it's just being really careful, about doing the addition, but otherwise it's straightforward. Subtracting matrices.
Exact same thing.
Mm-hmm.
You might have already answered this before. I feel like I've already asked it. If, say you have those two arrays inside of A, the two rows,
Mm-hmm.
1, 2, 3, 4, 5, 6, and then if you had the second row just had a 7 plopped onto it, if you would that make the whole thing invalid?
Yeah, you cannot add those.
Okay, so you
That's
wouldn't
right.
just add an extra value and just make it a 0
No.
and then add the 0 to the
Yeah.
Nope.
Maybe in JavaScript.
Yeah.
A matrix has to be internally consistent as well as consistent with the rules of the operation.
Yes.
So no tricky.
No. No. That's just the rule. If you're going to add or subtract matrices, they have to be exactly the same dimensions, or that's not a valid operation.
On the test, if something like that comes up, we just say not a valid operation.
Yep.
We-
Now, we're just doing simple A plus B, A minus B, but we could have a third matrix, and we could say A plus B minus C. And as long as those are all the same dimensions, could you do that? So we would sum A plus B first, and then we would take that sum and subtract C from it.
Do you have to do order of operations for something like that?
You would have to do order of operations,
Is it
but on the
like-
test, it's not going to be.
Do
It's
you have
gonna-
like A minus B times C?
Yeah, and that.
B times C and then minus it.
Yeah, yeah. So if you had A minus B times C, then you would do B times C first, and then you would do A minus the the product of B times C. Yeah. Okay, so on multiplication, the dot product. How are people with dot product? So if you're not comfortable with it, practice. I have a worksheet with matrix multiplication. Just do that. And if you aren't getting the answers right and you don't know why, then come talk to me. All right? That just takes practice. That's it. But does everybody remember the concepts? Multiply each row by each column. Yeah. Okay. Graphs, yeah.
What's the operator for scalar multiplication? Is that scalar?
Scalar multiplication, you would have a number times a matrix. So you wouldn't have like matrix times matrix. You would have like,
oh yeah, true.
yeah, you'd have like
what's the
3 times B.
yeah, that's right.
Just
What's,
like a constant, right?
what's the term for multiplying just like A times B, like dot product is invalid here, right?
No, you just have to shift it. That's
Actually, yeah, let's do this actually, okay? Let's say that
Translation.
B is transposed.
Okay. Is there
On the test,
Yeah.
don't assume that you need to transpose it. On the test, if it doesn't work the way it is, then it's invalid.
So that
Okay?
has to be specified as it's transposed.
It needs to be specified A times B transpose.
Yeah.
Okay?
Okay. Is there such a thing as like just I don't know what you're gonna call it, linear multiplication? Just
No.
Okay.
For a matrix multiplication, you do the rows by the columns, and the results you do in rows, right?
So you do the first row by each column, and those answers go in the first row.
In the first row.
Yes. When you do the second row,
They go in
the
second
answers
row.
go in the second row. Yes.
Yeah, you do row and then yeah.
Okay, what type of graph is this?
Weighted directional.
A weighted digraph.
Yeah.
Or a weighted directed graph. Yes, a weighted directed graph or a weighted digraph. And could you provide the adjacency matrix for it? Yep. Okay.
Fairly low.
It's just
1, 0, 0, 0, 0, 0,
Okay. So
0, 1, 1, 0, 0, 0.
so there's practice for this too. Okay, yeah.
Because it's going to be on Canvas.
Yes.
How do we type out information? Is there going to be fields, like actual fields in the field?
No, and that's a really good question.
Can we put a photo on
If we just do it
I don't know if you can upload a photo in Canvas in the
That's
answer.
just like the table thing in Docs.
Hyped and underlined. Yeah, I think
Does it have a table?
I think it does.
Yeah.
It does. Did.
Does it have a table?
I know that it had formatting. I know they had formatting and like the basic.
So
Yeah, like it seems like
if you, it just,
As long as it's readable.
it needs to make sense, yeah. So if you just did like, you know, rows of space separated numbers, I'd be happy with that. Do you know what I
They
mean?
don't align properly.
Oh, I see. Yeah.
Yeah. That's a really good question though, and I'll ask the question. I can't take a test to play with it. Like I want to go. I'll figure that out though, and it is, yeah, as long as it's readable. Like, you know, you could do it like this if you wanted to. No, you don't want to do that because that's really hard to. I mean, if you wrote it out on paper, right, and you went from the paper to writing that, then it wouldn't be hard, would it? So, I mean, definitely for this, I suggest doing these types of things on paper and then translating what you've written into Canvas. Don't try to just do it in, because math's not good. You're gonna make a mistake. Yeah. The edge list, you could provide the edge list too. Yeah. And if we have this, if we have a matrix, can you draw the graph? I don't think we're going to ask you to draw a graph in the test because how would you do that in Canvas? So I don't think you have to worry about that, but you should know how to do it though, okay?
You've got like little circles and
A line arrow B.
Yeah. Spend 2 hours trying to format a graph in Canvas. Don't do that. We wouldn't make you do that.
then hiding colors in the table and then you get to the next
Yeah.
graph.
Finding the shortest path between a source and any other point using Dijkstra's algorithm. Are you guys comfortable with that?
So the test would just write in the answer. That
But
one would just go
on the test, though, I'm sorry, say that again.
on the test we just write like the cost is this and then the path is like A, B,
Yeah,
C, D.
exactly. But I think on the test, there's a question like, find the shortest path that visits all nodes. Which I put some of those in my graphs review. The shortest path that visits all nodes. That's not Dijkstra's algorithm. Okay? That's not, but the graph is super simple. It's like really small. It's not like a big, giant, complicated graph with a million connections. It's like a small graph.
ABC.
So, on the review sheet that I made for graphs,
Just go not an arrow in the test. Just go like, no, not that one. No, not that one.
Just like write out all possible
I would just like
here.
figure out what the worst combination would be.
Find the shortest path that crosses all nodes in the path for B, for this one, and give the cost. So draw the graph and find the shortest path that visits A, B, C, D, and E, that visits all the nodes. No. So if we're saying the shortest path that visits all nodes, it doesn't matter what the first one is. You can start from any of them, but your path has to visit each node.
In general, it'd be smart to avoid the. It's not.
If the question says, you know, starting from this one, find the shortest path that covers all nodes, that you still can't use Dijkstra there because Dijkstra doesn't guarantee you visit every node. So, but this question, the way I asked it, which I believe is the way it's asked on the test too, is starting from anywhere. What's the shortest path?
So the order, the resulting order is not important, it's the cost that you're after.
Yes. So you want the smallest cost, but every node is in your path. Yep. A path that includes every node with the least cost. That's what this is asking. Okay? So if you draw that graph out, you'll see it's not complicated. You can just kind of like, there will only be like 1 or 2 possibilities to visit all nodes, you know? And then you just calculate both of those and that's the shortest. Yeah, you find the shortest. So, and that's what it will be like on the test too. It's not going to be a big graph. There'll be like, 2 ways or something, to actually visit every node, and you just figure out which one's the least expensive way. Okay? Back to this. Functions and relations. So being able to recognize from a picture what's a function and what's not a function. All you look for is that on the input side, each number only has one arrow going from it. Okay, that's what matters. So in this one, the first one is a function. Second one, not a function. Okay, because 2 has 2 outputs. And if we have a relation between a set of numbers and the set formed by adding 1 to each number, okay, that'll be a function. Yep, because for any number, if we add 1 to it, we're only going to get one answer. We're not going to get 2 answers. I did have a functions worksheet that's got, I haven't done it yet. Never mind. I'm working on that, so I'll give you some more questions related to this. One other thing I want to mention. There is some notation in here. This notation. It's very unattractive notation. Okay. You don't have to. It's only worth 1 point. So if you don't care, just leave it. But there's a question that expects you to understand this kind of notation.
Which one? Is it the one?
Yeah. So understanding sum, that this is a sum.
Oh, right.
Okay. And we're saying a sum from k equals 0 to k equals 4. I don't know why there's a k here and there's a j there. That's really... Oh, j squared, okay, is 0, 1, 2, 3, 4. Yeah, so k gets substituted here. So we start with k equals 0, 0, and we're squaring that value. I really think these should be the same. I think that's wrong. So these letters should match, okay? So what it means is that we square this value from 0 to 4, and then we sum that. This is a sum operator, and the answer to that would be 30. So recognizing that notation, and also notation like this. So this is A, and this is B, and C is the dot product. This is another notation for dot product. A times B, right? So C is going to be some matrix. And one way to represent that dot product is that we take the sum of the values in A at position ik, starting from k equals 0 to 3, times b kj. So it's just another way to represent that we multiply each element of the row by each element of the column, and then we add those together. Okay, so that's just a way to represent what we're doing there with some notation.
So AIK is A at the index of K, right?
Yes.
And
so yes.
BKJ, B at the index of J, or what?
So C00 equals A at 0, first position, or 0th position, and then first position, and then second position up to 3, from 0 to 3. So this is 0, 1, 2, 3, right? And B from 0 to 0, 1, 2, 3. So this J and this I is 0 in both cases. Okay, in both of these. So have a look at this section in Canvas and see if you can make sense of it, and if you can't, then come back and talk to me. Okay?
That's worth 1
But
point, right?
it's worth 1 point.
There you go.
Okay?
Where is I and J defined?
They're arbitrary
Well, why are they not just 0 if they're always 0?
because they change.
Because they can change. So if we're finding C00, but then we could be finding Z01 and then C10. So those numbers change according to which
So it's CIK.
element.
So it's C00, but it's also CIK.
CIJ.
J.
Yeah.
Yeah, J. CIK.
CIJ.
Okay.
Yes.
If I see that one.
That shouldn't be CIJ equals that.
Yeah.
That algorithm.
If I see
C00 wouldn't have been that. C00 would have been it would have been AI0 multiplied by B0J.
Yeah, so let's look again. So the first one would be
C00 should be AI0.
C00 would be A.
Oh no. It wouldn't.
Yeah, it would be A0, 0, 1, 2, 3, and B 0, 1, 2, 3 with 0.
Yeah.
Yep.
Because K is going to change.
K is going to change. K goes from 0 to 3.
Because
Yep.
the number of elements.
And because in A we're going across a row, and in C we're going down a column. So that's why they're switched between the two.
And then C0 next to. Yeah. So that's not 4. It's 3.
Yes, that's right. So just some nice mathematical notation. And then what we covered today with the properties of relations. So reflexivity, symmetry, and transitivity. Whether a relation is reflexive, symmetric, or transitive. Understand what those relations mean. And then be able to answer a question like this. Like this one. The properties of the relation described as greater than or equal to.
Would you say reflexive A equals B,
Mhm.
symmetric? How would you describe symmetric then? A, B, B, A?
Yes.
And then transitive
A, B,
A, B,
B, C, A, C.
Can you use those like relational symbols?
You can.
Can we use like hooks? No?
So greater than or equal to, what are the properties of greater than or equal to?
Reflexive and transitive.
Yeah, is that clear to everybody? Reflexive and transitive. Same for less than or equal to. Hmm? Okay, cool. Symmetric is the toughest.
Yeah, I'm trying to like other than equal, what's something that's symmetric or equal?
I can't think of something that's symmetric. Symmetric is hard.
If you had a set of
I can only think of non-math examples of symmetric.
Times -1. Is that symmetric?
Ah, times -1.
It's symmetric, right?
It is symmetric, isn't it? Because 1 times -1 is -1, and -1 times -1 is 1. That is symmetric. Good job, Matthew. Yeah, times. Yeah. Cool.
good thing is we can tell that number of tests.